Any idea what do we call a relation? I'm related to you guys. How? What's the relation between us? Teacher, student, huh? You guys are related because you are both taking one course. So the relation is just getting just the 270A course, or maybe you're the same major, okay? So this is what we call relation. So it's like really function. It has one input, one output. So there is a relation which we call it equation. If it's in math version, we call it equation, but there's a relation between X and Y, but there's no condition on that. For functions, if you remember, like just saying Y equals X squared, it's a function. Maybe X equals Y squared is not the function because it passed it passed your vertical line test, or your second component shouldn't be repeated, right? So those things was really special for the functions, but for relation, no. It's just really any set of ordered pairs. No relation, no test, nothing. It's called relation. So if you have one X as inputs, we had one Y as output. So we have domain and codomain without any condition. So this is just really a simple example, like just here says, there's a relation of the students to the courses. So the left column are the name of the students. The right one is just the course that they are taking. So Bill is related to the computer science, means Bill is taking computer science. Or just maybe Beth is related to the history because he's taking the history course. So the relation, is just between two sets, any set to the other set, and it could be a list of X's to the list of Y's without any condition. So the first one is called domain, the next one is called codomain, exactly the same way we have had for the functions, okay? We have two kinds of relations. It could be binary relation, which is require two elements of X and Y. It could be unary relation, which is only one. So if you want to just back to the set theory, you can say like just union. So if your union is the relation, you need A and B, then union of A and B. If intersection is your relation, so you need two sets to make intersections of two sets. So those are binary. But if you just want to have complementary, no, it's really one set, right? So it's unary because it's only one set as input, and then you make the complementary. Okay, same thing for like functions. If you have compositions of two functions, you have to have two functions to compose. But if you have inverse of a function, no, it's just really one function and inverse. So that's just how many inputs you have and how many output you have. So if it's related between two of them, is called binary relation. So what is the letter R typically for making the relation between two sets? One of them is X, the other one is Y. It typically has Cartesian product, so it's ordered pair. One X's are coming from the first set, one Y's are coming from the second, and the order matter. So you can't switch them. So then X is coming from the X's, Y is coming from the Y, when X and Y are related. If you want to say X and Y are related, we just put ordered pair of X and Y is in R as a relation. Okay, that's how we know it, right? Or you can write it like this: X is related to the Y. You put X to the left, and R is the relation between them. Y is to the right. So that means X is related to the Y, either by this way or this way. So that's how we can say X and Y is related. Again, you can say like Dr. Nargesi is related to the just Gabriel. How? Because that relation is being student teacher. Okay.
This is a general statement, so it doesn't say anything about how they're related, just that they are related?
They are related. It could be any relation between things, between sets, between, I don't know, students, cars, right? So as I said, function that we've seen before is very special case of a relation. Relation is more general. It doesn't have any condition. So if you remember, function is defined from one set, which we call it domain, the other set, which we call it codomain, is a relation that was these two satisfy, right? These two properties satisfy. So your X's are coming from the domain. For every single X from the domain, there should be exactly one. There should be exactly one Y in the codomain, that X and Y is in that relation, in that function, okay? So that was just special for being a function, but relation doesn't have anything. doesn't have any condition, okay? For the example that we have had as a table, if we call it T table, that's true exactly as a T table because you have the set of X on the left side, the set of Y on the right side. So in that example that we did, we saw on top, your X's, the set of your domain, the set of your inputs are just the name of the students, the Y or your codomain was the set of the courses that they are taking, and that table was the set of ordered pairs. So you can write the first student with the course that's taking X, comma Y, X, comma Y. You can repeat all of the relations as ordered pairs, okay? So when we have the ordered pair of Beth and history is in that relation, that means Beth is taking the history, right? So B is taking the course of the history course, okay? So you're having just with the numbers, very simple example with the numbers. If your X's or the first components are 2, 3, 4, the second components or the codomains are 3, 4, 5, 6, 7, so then you can define one relation. So this is X and Y is related by this just example. Like 2 is related to the 4, 2 is related to the 6, 3 is related to the 3, 3 is 6. And you see, repetition doesn't matter. For relation, we have no condition. It's more general than what we call function. Or 4 is related to the 4. Do I have to make sure it's taking every element of the domain as it was in well-defined function? No, I don't have to worry about that. Well-defined function, if you remember, all of your numbers from the first set must have one output, but here we're not worried about that. So it's just a relation. Okay. The terminologies or properties that we want to practice are 4 properties. Okay, so there are 4 properties here. And if we put 3 by 3 together, it has a special name. So first of all is reflexive. So one of the relation is reflexive relation. So what is the reflexive relation? For any relation that X is related to the X. If anything is related to itself, that's called reflexive relation. So very common example of relation is inequalities. X bigger than equals, X less than equals, X even equals to the Y. Those are just really common example for the relations that we can practice with these 4 properties, as I said. So in this relation, you can use it still the same way. If you remember, your function was like this. You just define R, then this is where you put your inputs, your domain. Actually, it says related X is from X to the X. So then I have to go from 1 to 1, 3, 4. Okay, from 1 to 3, 4 to 1 to 3, 4. And then the relation says X and Y are related if and only if X is less than equals. I can just use different notation. We can say it like this, or you can say it like this. And then this relation is X to be less than equals Y. Okay. So if your every single elements of 1, 2, 3, 4 is related to itself, means when you say X and X is related, X and X related means 1 is less than equals 1, 2 is less than equals 2, 3 is less than equals 3, 4 is less than equals 4. Yes, that's true. So that means this is a reflexive relation. So these are all true inequalities. So that means this is reflexive inequality. This is, reflexive relation, okay? This is fine? Does it make sense? Question here. Any question here? The next property for relation is symmetric. Actually, I have one example which is not reflexive. So this relation, this example right over here, that's just the set of ordered pairs that you have here. So A is related to the A, B is related to the C, C is related to the B, D is related to the D. And your domain and codomain is the set of A, B, C, D. So is it reflexive? If it's reflexive, you should have A, B, B, C, C, D, D. That's how it's reflexive, which you don't have, right? You don't have BB, you don't have CC. So that means for one counter example, you can say B is not related to the B, or you can say C is not related to the C, so then fails, right? So this is not reflexive. Does it make sense? Even for previous example, if I remove that equality sign, if your X less than proper inequality, X less than Y, that doesn't satisfy the reflexive property, right? So it's not reflexive anymore, right? Because it's one is not less than one, is less than equals one. So that equality is required to be reflexive. Make sense?
So for every ordered pair, it must be that to be reflective?
For every ordered pair, if it is based on whichever domain that you choose, if you have all of the elements by itself, A by A, B by B, C by C, D by D. If it's numbers, 1 by 1, 2 by 2, 3 by 3, 4 by 4. Okay? So what I was explaining, I can just rewrite it over here. What I was explaining, if I have had the example, yeah, they need to wake it up. So this is if you have X and Y to be related, and that relation to be X less than Y without that equality sign, and then your domain and codomain to be 1, 2, 3, 4. So this relation is not reflexive anymore. So you can bring one counter example, right? So you can bring one counter example because 1 is not less than 1. This is false. So this is not reflexive anymore, okay? But the previous one was with the equality sign. 1 is less than equals 1. That's a true statement. But this is 1 less than 1, which is false statement.
Is it supposed to be X? Because I see.
Oh yeah. This one. Yeah. You mean this one, right?
Yeah, at the top too, because I only see X.
The definition,
Yeah,
right over here.
Yeah.
No, it's defined.
X, Y.
Yeah. That's how the relation is defined. So the original relation is defined to be X is related to the Y if X is less than Y. So that's how we have definition of what the relation is. Then we have what, according, these are given, right? So according to the example, then we have, okay, so what are the inputs and outputs, which is 1, 2, 3, 4. So then we have just, if the question asks me, I need to complete the question, like just saying is or defined by X less than Y reflexive. So then let's reflexive. So then your answer is no. And that's one counter example because X is not related to the X in any of these relations, right?
Yeah, I'm just a little bit confused because it says the ordered pair X, Y, but I don't see Y at all. So like that's not.
What do you see?
I don't see the set Y. So like that's.
Oh yeah, so your relation, okay, so that's, as I said, because it's, as I just mentioned, the domain and codomain, for the same reason, for the same example right over here was the same. So you're having only, your relation is defined from the set of X to the set of X.
Okay.
That's why.
Okay.
It's the same set. It goes to the same set. That's why it's given only one of them. No Y. It could be different. It could be really different. Okay. Any question here? Okay. The next property is called symmetric. The next property is called symmetric. If you have X related to the Y, Y must be related to the X. So if any relation X is related to the Y, so then Y also is related to the X. Like a teacher-student is not symmetric. If I'm your teacher, you're not my teacher. It could be in some point, right? So soon after 4 years, you can be a teacher, but I have to be a student again, right? So that is just not symmetric, okay? And again, the good example is just the same inequalities, right? So if 1 is less than equals 2, not 2 less than equals 1, right? So this is false. So that's a good example. It's not symmetric equation. So that is not a symmetric relation, okay? So one more time. What relation is symmetric? For every single X and Y's, if you have X and Y related, then Y and X also is related. Okay, for every single X, if your X is related to the Y, it means X is first, Y second, then the other way must be true also. So also Y is related to the X. That's all. That's what we call symmetric. So for this just example of relation which is given by the set of ordered pairs, you can see in the first one, one is related to the two, two also is related to the one. Okay, so this is perfect. That's exactly what we call symmetric. Okay, X is related to the Y, Y is related to the X. But then in X, 3 is related to the 4, but 4 is not related, or 4, 3 is not part of my set. So then it's not symmetric. Okay, so 3 or 4, 3 and 4 is in the relation, but since 4 and 3 is not there, so that's not a symmetric equation. That's not a symmetric relation, okay? Make sense? So I have another example which is given again, similar to the, I think we have had the same example, yeah. The same example that we have had on top for being symmetric. Okay, can we check it? So if A is related to the A, it doesn't matter if you switch it, A and A still is the same. So it still is fine. You have to check it one by one, okay? If B is related to the C, so then you must have C and B, which is fine. So, which is fine. If C is related to the B, B and C is related, this is fine. And then same thing. If D is related to the D, switching D and D is the same thing. So is it symmetric? Is this symmetric? For every single elements that you have it in your set of ordered pairs or in your relation, the reverse is also part of your relation. So this is a symmetric one. Okay?
You don't need to double the D with D. Just one is enough.
That's a set, right? So the set repetition in the set doesn't make sense, right?
Yeah,
so it's a set of ordered pairs. You can have 10 of them or you can have one of them. It's the same meaning.
Okay.
Relation is set of ordered pairs. So this is a symmetric one. So one more time, this is just really universal, right? So this is a universal. If you bring one counter example that doesn't work, so you disprove it. So this is universal. It says for every single X's and every single Y, if X and Y are related, then Y and X must be related. Okay, so this is called symmetric and is universal. So then if you want to negate it, if you want to disprove it, there should be only one X and one Y that are X and Y are related, but not Y and X is related. So then it's enough to just say, this is not symmetric. Okay, this is not symmetric. Like our example right over here, we have had only one simple example, one simple case that 3, 4 was part of relation, but 4, 3 wasn't. So then you stop. That's not symmetric. One counter example would be enough to disprove universal statement. Okay. Question here for being symmetric. So you can add the example, say one of the other example you can add over here, the relation of X is related to the Y if and only if X is less than equals Y is not symmetric, right? Because that's what in real number is true, right? So in real numbers, if you have one less than that's always one way growing this is increasing numbers in real numbers. If you're having 1 less than equals 2, that's true, and then 2 less than equals 1 is false for sure. Okay, there are infinite many examples to bring why is not symmetric. A little bit more challenging case, it's called anti-symmetric. A little bit more, it's called anti-symmetric. Okay, it says you should have X is related to the Y and Y is related to the R. So that means, sorry, Y is related to the X. Okay, so it means you have both of them in your relation. That's just your P. That's your given information. Then your Q, the Q has to be X and Y must be the same. That's what we call anti-symmetric. And again, this is really the best example for anti-symmetric. If x is less than equals y and y is less than equals x in real numbers, what I can say? X and y must be the same number, right? This is impossible. You can't have in real numbers x to be less than equals y and y to be less than equals x unless x and y are the same. Okay, so that's a really good example for anti-symmetric. That relation is a good example for anti-symmetric. Okay. Question here? Question here?
If you were to replace the less than or equal to with equals, does that also set
Without.
the same condition?
Without equal.
No. Just you replace that with equals. So x is related to y, but y is kind of arbitrary in this case because x equals x. Does that make sense? Or
No.
am I thinking too
No,
much
no,
about
no,
it?
no, no, no.
No? Okay. Got it.
Question. Any other question? Here. Transitive. What's the transitive? X is related to the y is related to the z, then x and z is related, okay? So it's like this, x is related to the y is related to the z, and then you just eliminate the middle one, x and z are related, okay? Which works for inequalities, right? Like saying x is less than equals y and y is less than equals z. Can I say x is less than equals z? That works for numbers, right? So this is clear for our relation of less than equals, or actually the same for bigger than equals. So it's the same. We don't have any example bar here because we have to put them together, okay? So if you have any relation, for now, what we call partial order. So what is partial order? It's the one that has 1 reflexive, 2 anti-symmetric, 3 transitive. If you have one relation that is reflexive, anti-symmetric, and transitive, is called partial order. Okay? Not symmetric, anti-symmetric. If you replace symmetric by anti-symmetric, that's called equivalency. Okay, that's the next one. So we are looking for some examples for what we call partial order relations. So that means I have to prove it's reflexive and anti-symmetric and transitive. So is partial order. Okay. And again, this is just something wrong here. So when you have the same relation that we started the example of less than equals, is it reflexive? Less than equals is reflexive. That's for integers, but it's okay for real numbers too, right? Is reflexive, is anti-symmetric, and is transitive. So this is a good example for partial. Actually, that's the only reason that we call this one partial order. So the only reason that this relation with transitive, anti-symmetric, and reflexive is called partial order because of that inequality. That inequality because it gives you order of real numbers, because it gives you the numbers on the real line to be by order from the smallest to the biggest, right? Okay, so one more. The divisibility. It says, that's a notation. Have you seen this notation? We always write with the just words. A is divisible by B. A is divisible by B is what we always write. So that's a notation in math notes or is just any LaTeX anywhere that we type to say A is divisible by B, which is the same as there exists one T, B is equals A times T. Or you can always use the words, or you can just write this notation. It's really one simple vertical line, okay? I'm going to just really see one by one. This is, which example is number 2, right? This is number 2. So come over here and write number 2, which is A is related to the B if and only if A divides B. A divides B, which this is the same as there exists one scalar. There exists one scalar. Actually, this is all for integers or real numbers. For integers, only for integers. Such that B is T times of A, okay? Reflexive. How do I show this is reflexive? I have to show for all A to be positive, making sure I'm just writing the same, yeah. Positive integers, for all A's to be positive integers, A always divides itself. Is it true? Because there exists the T equals 1 such that B equals 1 times, I should say A, right? A equals 1 times A, right? So it's anti-symmetric. For all A and B to be positive integers, if A divides B and B divides A, then A and B must be the same. Is this true? Is this true? A divides B, that means there exists one scalar such that B is that T times A. B divides A means there exists something such that A, actually I have to choose different T1 and T2. This is T1 and T2. Okay, can I say this means A and B are the same? What do you think? Think about numbers. Thinking about numbers, okay?
Well, B is divisible by A, then that means B has to be bigger than A.
Uh-huh.
Bigger than or equal to. And similar, we can say if A is divisible by B, it has to be bigger than or equal to B. And for both those relations, or I shouldn't use relations, but that's the word we're using here, but for both those statements to be true, it would have to be equal.
Because this can't be fractions, right? If this was fraction, you can just say that T1 is reciprocal of T2, probably, huh? So it works with the fraction. That was just a little bit hard to just show it, or it fails to show. But as we have just the discussion over here, when A is divisible by B, this is the same as saying B has to be a bigger number than A, and here also A has to be a bigger than a B. So then that's possible only if A and B are equal. That's possible only if A and B are equal, otherwise it's not possible. Make sense here? Make sense? And transitive says for every A and B and C to be positive integers, if A divides B and B divides A, then, B divides C, then A divides C. So you can say the same thing. A divides B is the same as there exists some integer that B is T1 times A. B divides C means there exists one integer that C equals T2 times whichever B is, okay? So what I'm looking for? I'm looking to just say C equals T2 times B, which B replaced by T1 times A from here. So then C equals, put these two together. So this is the same as A divides C, right? This is the same as A divides C. To be something like only one T. So then A divides C, okay? So that's why this divisibility is one partial order relation. Divisibility is partial order relations, okay? Partial order. Make sense? Question here? What was my next example? Inclusion, subset. Inclusion or subset also is, it's very similar to inequality, right? Do you agree? X is less than equals Y is very similar as far as the properties. A is subset of B, huh? So it says inclusion or subset is also partial order. It's also partial order. So it's transitive. It's transitive, anti-symmetric, and reflexive. Is it? Is it reflexive? Is always A for, I have to write it, for all A's to be, I have to call something else because this is also called A. For all of the subsets which are in your power set of the A, can you say S is always subset of itself? That's true. Anti-symmetric. So for every single, I'll say S sub 1 and S sub 2, which is in power set of the A, if S sub 1 is subset of S sub 2 and S sub 2 is subset of S sub 1, then S sub 1 and sub 2 must be the same. So that is anti-symmetric. And then transitive. For every S sub 1, S sub 2, and S sub 3, from the power set or set of all subsets of the A, if you have S sub 1 subset of S sub 2 and S sub 2 is subset of S sub 3, so then you can say S sub 1 is subset of S sub 3. So this is called transitive. Okay?
Professor?
Mm-hmm.
All of that makes sense, but I wouldn't be able to get that from the statement. Could you read the statement for number 3, just like how you would read it out loud? Yes.
Transitive, number 3, you mean transitive or what?
No. The question, read the question.
Question?
Yeah, so like, I'm not sure how to read this. Set inclusion.
Set inclusion means just subset. So set inclusion is the relation, the name of relation. Name of relation. Name of relation is set inclusion, which is subset, which is the same as subset. Okay?
So it says
On
actually continue.
I'm okay by now. So then set inclusion, which is subset on power sets. So means your inputs are from power set of A to the power set of A. So your X and Y, or if you want to make ordered pairs, is just a set of subsets. So then your domain of that relation is power sets. The all possible power set is all possible subsets of A. Is that okay? Do you remember this power set?
Yes, I remember power set, and I know what the subset symbol means, but I'm just having a little bit of trouble figuring out how you got that domain and codomain. So we're saying.
So that means-
The power set of A to the power set of A, will that always be the case?
So that means if A is related to the B is defined, A is subset of B. The relation is the being subset. So this, if you remember for the function, this is your set of x's, this is the set of y's. And that's a relation between x and y's. So what's a relation? Means A is subset of B. So if you have an ordered pair of x and y, to be in that relation is the same as x is subset of y. Make sense? I don't see your confusion yet, sorry. If you want to repeat your question again or no?
Yeah, I just feel like it's not worded in really in a question. Like I'm
No,
not.
there's nothing worded over here, unfortunately. It says, these are the examples for partial orders. So this is this list of examples for partial order relations, okay?
I was asking you a question, that's why I was wondering.
So
You're just
that's
giving
that
examples.
example number one, example number two, example number three.
Okay.
So this is the list of the one that we already know they are partial orders.
Okay.
For example, can I see the consistent like that?
Do you have a question? Or you just,
Yeah, if it's an example, that makes a little more.
okay. So this is exactly what we have done right now, and we showed all of these properties of reflexive, symmetric, and transitive for this divisibility. I have another expression over here before moving to what we call equivalency. It says A and B are comparable. So you can just define two letters or two inputs or two outputs to be comparable, because either your relation of x is less than equals y works, or the relation of y equals x works, right? So not both of them. Either of this one, for example, for the relation that is less than equals, either of these two is true. Okay, so then that means you can compare them. So if I give you any two numbers, you can compare whichever is smaller or bigger. Okay, this is just what we call comparable relation. This example that we have had for less than equals is called totally ordered. So if you're having, one more time, reflexive, antisymmetric, and transitive plus comparable, these four together, then it's called totally ordered. Okay, so partial order, it has only three properties, and if they are always comparable, so there's four of them, that's called totally ordered. Okay, that's called total. That's what we know for integers, that's what we know for real numbers. They are comparable, right? So those are totally ordered relation. Totally ordered relation. Okay. So a totally ordered subset of the partial ordered set is called a chain. Okay, so if you have one subset of your partial order which has all elements comparable, so that's called a chain. For divisibility, we have a good example for a chain, because as you see, this is one example. 1 divides 2, 2 divides 4, 4 divides 8, 8 divides 16. So that is what happening here. That's, we call them chain, okay? So because they are related back to back, they are making, for that transitive property, they are making a chain, okay? So what's again? You're having what we call partial order, because we proved divisibility is partial order, plus that comparability, or what we call total order. So then any total ordered subset of any partial order is called a chain. Okay? Make sense? Question here? Any question here?
I'm still a bit confused for the definition of comparable and totally ordered. Can we do can you show an example of what particularly what might be helpful to me is what makes divisibility not
Actually, divisibility is totally ordered.
ordered? Oh, it is.
Yeah. So you have to find something which is not partial order, or which is not comparable. I think we have it in the book. Okay, so let's open the book and find it out. Okay. So this is one thing that we can find in the book. Do I have any example here? I think. I don't know whether I have it at the end, but I can add one more over here. This is one example. It's what we call partial order set. Briefly, we call it PO or POSET, partial order set, okay? Which is the set of natural number with the less than equals. This is a totally order set. And then the subsets for all natural numbers, the subset I have is 1, 5, 25, and 125. And then with the divisibility set, so then A is divides B is just a relation. So same thing that we know, there exists one scalar that B is scalar times of A, or A divides B, okay? The set of this also is partial ordered. Okay, so then what's happened for the chain? 125 divides 25, 25 divides 5, and that's how it is. Okay.
When you say 125 divides 25,
Because that was, sorry, 1 divides 5, 5 divides, so it's backward. Sorry. It's back. 1 divides 5, 5 divides 25, and 25 divides. Thank you. 25 divided. I have another example, which is partial order set of 1, 2, 4, 18, and 16. And then if you want to make it briefly, we don't want to write the whole sentence like this, we can put it comma with the relation, okay? So comma, this is the relation. What's the relation? Divisibility. Yeah. Okay. The question asked me, is this totally ordered set or not? Is this one a totally ordered set or not? If you start from the beginning, 1 divides 2, 2 divides 4, 4 divides 16, but not 18, right? 2 divides 18. For every single element you choose, for every pairs that you choose, they must be comparable. What do you think? Is this satisfy that relation? So let's say you choose the pair of 4 and 18. Okay, so one more time. For whichever x and y that's coming from this set of 1, 2, 3. Okay. Either x must be related to the y, or y must be related to the x, which that relation means division. That relation, sorry, divisibility.
I think I was confused in that paragraph because it said just x, let's say, greater.
That's it. Yeah, that's
I
just
didn't realize it meant just whatever relation.
what's the relation. Yeah, that's true. Okay, now it makes sense, right? So this is not a total order, right? This is not a total order because I have one example, I have one counter example that is 4 and 18, and they are not related. It says either 4 must be related to 18 or 18 must be related to the 4, but none of them are true. Okay. Okay. The answer is no. Question here. I have to go back where I was because this page was so slow. It didn't show me what I want to find. Okay. Yeah. Move on. This is similar to the function. You can define the reverse, right? So if your x and y is in your relation, you can make it inverse of your relation. So then y is related to the x. So you can make the reverse for any of these relations. So like saying your example, your domain is x and your y just different numbers. X is related to the y is defined again divides. X is divides y, that's an example. So it says 2 divides 4, 2 divides 6, 3 divides 3, 3 divides 6, and 4 divides 4, okay? So this is one relation. So then what's the inverse of the relation? So obviously from the algebra classes, we know what, right? So we need to switch it. So from algebra classes, we have learned what the inverse mean. If x is related to the y, y related to the x is in the inverse, okay? So if you're just reverse it, it's not the same relation anymore for sure, right? It's not the same relation, it's reverse of that relation. So it's reverse of that relation. So if it was x divides y, now y divides x for the R inverse, okay? Is in R inverse. Make sense? One more relation. Is it okay now? Reverse. Make sense? And then another operation that we can have between two relations, very similar to the functions, is compositions. If you have two relations, you can get the composition of two relations, okay? So your R1 is defined from X to the Y. So one more time, this is like this, X to the Y. And then your R2 is defined from Y to the Z. So then you're having the same notation. R2 compose with the R1 is from X to the Y to the Z. It's from X to the Z, and that's just similar to what we have had for the functions, okay? But this is by ordered pairs. This is one example to practice. This is one example to practice. We have many of those in homework, okay? So it says, if your R1 is defined by this set of ordered pairs and R2 is defined by this set of ordered pairs. So for example, it says, what is R2 composition with the R1? Okay, the answer is right over here, but I want to just do it step by step, okay? So obviously it has to be the set of ordered pairs. There's nothing to do with the union, with the intersection, with nothing, right? So it's a brand new operations, right? So if you want to define, what was it? R2 compose with the R1, okay? So your inputs for R1 for this example is, clean it up. Your inputs here for this example is 1, is 2, is 3, and that's it. Your output is 2, 6, 4, and 8. So this is your set of inputs or your first component. This is the set of output for the second component, okay? So if you start with the R1, because this is inside, so you start with the R1, so that means your input is 1, okay? So you're having 1 and 2, which is in R1. So then you have to look for the 2 and something in R2. Because first is R1, which transfer 1 to the 2, and then is the R2, which transfer 2 to the U. Is it okay? Let's try one more time. So 2 to the, what was it, U? So then one transfer to the U for compositions, okay? So there's actually 2 of them. We have to try one more time. So we have 1 and 6, which is related in R1. We have 1 and 6, which is related in R1. And then next term is 6 and what? Related to the R2. Where is R2? It has 6 and T. So that's the T. So this means you're having 1 and T also in the composition. Make sense? Let's try one has no more. One has no more. So we go to the next term. Next term is 2. So you have a 2. You have a 2 right over here. So by this one, 2 is transferred to the 4 by relation number 1. So 4 transferred to what by relation number 2? Actually, we have 2 possibilities. For either transfer to the S or T. So then you can have 2. You can have 2 and what was it, S, or you can have 2 and T. So 2 and S, 2 and T. Is that okay? Do you follow? One more time. You're having 3s, actually 3 times. We have to try all. 3 transfer to the 4 by relation number 1, 3 transfer to the 6 by relation number 1, 3 transfer to the 8 by relation number 1. Okay, so then you have to look for what 4 is transferred with the relation number 2, what 6 is transferred with the relation number 2, and what 8 is transferred with the relation number 2. Okay. In relation number 2, 4 transfer 2 times to the S and T. So then you have to have S or T. So that gives you either 3S or 3T. And then 6 transfer to the T only, 8 transfer to the U only. So that means you're having 3 ending with the T, which is repeated, 3 ending with the U, which is not repeated. 3S, 3T, and 3U. Okay? Is it fine? Does it make sense? Question? Any question here? Move on, okay. This is a little bit long. I'm going to skip this one. We have actually 1 extra credit even for practicing these properties. It's saying if you have 2 relations and we have operations between relations, because it's just really the sets, right? So we can union the relations because that's 2 sets. You can intersect between 2 relations. You can compose between 2 relations. So those are operations. Actually, we can subtract too, but we don't have subtraction here. So we have union, intersection, and composition between 2 relations. So then the question is, if number 1 and 2 are reflexive, is it after union, intersection, or composition is still reflexive? The question is, if you're having, for example, symmetric. If you're having symmetric, if you just do the union, still is it symmetric? If you do the composition, does it save your symmetric relation or not? Or the same for transitive, okay? So those are part of them, actually. I think 3 of them are here. The rest of them is in your extra credit. So which you have to see whether operations of intersection, union, and composition hold your properties of transitive, anti-symmetric, symmetric, and this is just a few of them. This is just a few. As I said, 3 of them is here. The rest of them is in your extra credit. Okay. So that one needs more time. I'll give you time to think about it, and then we'll try it in next class, okay? And then you have the extra credit part also. This is what we can finish it right now. What is it? So there is another name for the relations that's more popular than the first, which is partial order, which we call it equivalency. We've seen what we call equivalency, right? So we know what do we call equivalency as logic, as set theory. So we know what they are. The only thing is here is as relation, okay? So if your relation follows reflexive, symmetric, and transitive, that's called equivalency, okay? So one more time, reflexive, anti-symmetric, transitive, partial order, reflexive, symmetric, and transitive is called equivalency relation, okay? So you just switch the symmetric and anti-symmetric between what we call equivalency and what we call partial order. Make sense? This is an example. This is an example that the set of ordered pairs is on your hand. Your set of inputs and outputs is from 1 to 5, 1, 2, 3, 4, 5. So for being reflexive, so you have to check if you're having 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So that means this is reflexive. And then for symmetric, if 1 is related to the 3, 3 also related to the 1. If 1 is related to the 5, 5 also related to the 1. If 2 is related to the 4, 4 also related to the 4. 4 also related to the 2. What else is left? So if 3 is related to the 5, 5 is related to the 3. So this is symmetric, okay? This is symmetric. So this is for symmetric. For transitive, okay. So like here between these two, 1 is related to the 1, 1 is related to the 3, gives you 1 has to be related to the 3. Yes, that's true, right? Like just saying between these two. 2 is related to the 2, 2 is related to the 4, so then 2 is related to the 4. That works. Okay. Which one has a 5? Like saying this 2. 1 is related to the 5. 5 is related to the 1. What else? What should be the conclusion for transitive? 1 is related to the 1, which works, right? So you can try more, right? So your 1 and 5 is related. 5 and 3 is related. So you should have 1 and 3. You do have 1 and 3 over here. Okay, do you see? Yes, please.
So for reflexive, symmetric, and transitive, does it have to be applicable to the entire set?
Entire set, yeah. Entire set.
So like reflexive, not all those elements are reflexive.
Which one is not?
Or like 3 and 1, 3 and 5, 4 and 2.
No. What does the reflexive mean? Reflexive mean whichever element is related to itself. It has to be both the same.
Right.
So 1 and 1 is 2 and 2, 3 and 3, 4 and 4, 5 and so 1 and 3 is nothing to do with reflexive because they are different numbers.
Right. So I guess what I'm saying is, does the entire R have to be that way in order to be reflexive? Or see, what you're saying is just part of those elements are reflexive. Be like 1 and 1, 2 and 2, 3 and 3, 4 and 5. That's all you say, and that's reflexive.
Because that's just what the set of all possible inputs are. Yeah.
Right.
So because your relation is defined from 1 to the 5 to 1 to the 5. Okay. So that's all possible reflexive we can have because we have only 1 to the 5. Okay. Move on. Do I have time? Yeah. Move on. So as we just, I think, mentioned somewhere, this is not symmetric, right? So X is not related, X less than equals Y. Y is not necessarily less than equals X unless they are the same. So that's not symmetric. So then the relation is not equivalency relation. The relation is not equivalent. It's transitive and reflexive, this relation, but it's not symmetric. So this is not equivalency relation, okay? Same example that I have had on top. So one more time, we know it's not reflexive. So that's stop, right? So if it's not reflexive because BBCC is missing, so then it's not equivalency. You have to stop there, right? First. This one? So if you choose any of these elements, 1 less than equals 2, so you must have 2 less than equals 1 also. So for any relation of X and Y and X must works too, but it doesn't, okay?
It would be equivalence relation if that condition X is less than or equal to Y, wasn't it?
So whichever, yeah, so this depends on what, for every single problem, domain, codomain relation must be given, right? So I can't guess it. So if you're having like just any different type, so give me an example which is equivalency. I can say equation for sure is equivalency, right? So equation. So if it was for all of X, Y's in R, or real numbers, then X is related to the Y is defined X equals Y. So obviously this is one equivalency that we know. Or actually those mods that we've seen, they are all equivalency relations in any mod, okay? Makes sense? This example, again, these are examples exactly we have had it on top. We tried it with the partial orders. These are repeated for equivalency. So when one of them fails, which wasn't really reflexive, so that can't be equivalency. One of them fails, okay? That can't be equivalency. I have one expression and then I'm done, okay? So one expression. For equivalency, we have something we call it class of members. class of elements. The notation looks like this exactly. This is the notation. So we can write the set of all elements which is related to only one single element. Okay. So we can write the set of all elements which is all related to only one single element. Okay. So for this modulus, that was really the best example you can have. So like saying if your relation of x, related to the y is defined, just to make it easy, x is related to the y by mod 2. Okay. So what's the class of 2? Is the set of all x's which x is related to the 2 in mod 2. What are them? All even numbers, right? And then if you just say class of 1, so it's the set of all x's which has remainder of 1 in mod 2, which is the set of all odd numbers, right? So on. Okay, so when we have modulus, then classes make sense, because for like just the set of, when you're talking about dividing by 3, so you have class of 0 remainder, you have class of 1 remainder, and then you have class of 2 remainders, and that's it. So the whole numbers, real numbers, sorry, integers are dividing to 3 classes. Either they are all remainder of 0, 1, or 2. So this is by definition of being equivalency relation, then we have class of equivalency, okay? We have more examples next class, okay? Question here?